Hello, everybody. Good afternoon to those in Europe. Good morning to those in the US, and good evening to those who may be joining us from the East, Middle East, and Far East. Welcome to this webinar. This month's webinar has got the title of Understanding How the UK and the European and the US process industries use hazardous area classification. Just let us introduce ourselves to start with. This webinar will be given by two presenters. Myself, who is Andrew Fowler. I'm currently the Technical and Operations Director at Sigma in our headquarters in Winchester in the UK. And you can see from this short biog that I'm getting old in years, and I've worked in process safety, both in terms of chemical manufacturing positions on manufacturing sites. I've also been within the UK's Health and Safety Executive as a process safety specialist inspector, and also in process safety consultancy. So as I say, 40 years experience in this topic, as well as many other in process safety. And we're joined also today by Andrew LaFlash, who is one of our colleagues who's located within our US operation. Andrew, can you introduce yourself?
Yep, Andrew LaFlash, chemical engineer by training, got my start in industry and LNG production before making the switch over to process safety. And I've since spent 6+ years in a variety of roles, from company process safety representation through to consulting and assistance with third-party audits.
Thank you. So what we'll be going through over the next 45 to 60 minutes, hopefully we'll look at this subject of hazardous area classification from the point of view of both flammable gases and vapours, as well as combustible dusts. And we'll talk about what hazardous area classification is across the two nations and how that then requires us to select appropriate equipment. But just to start with, just to let you have a little bit of a sales pitch first for those of you who are joining us for the first time, so just so you can get to know Sigma-HSE in a little bit more detail. So we have a global presence. We've got headquarters in Winchester in the UK. We also have offices over in a number of locations in India and also in New Jersey in the USA. And you'll notice that not only are we a process safety consultancy, but we have process safety laboratories as well, both located in Winchester and within India. I apologise now if you hear banging or drilling occurring, you can get those over. If you manage to hear some background noise, that's because we've got the builders in making some refurbishment to the laboratories and extension of those. So hopefully it's not too much of an issue for you. So that's where we are. What do we do? We're basically experts in anything to do with process safety. So that's consultancy basis on all aspects of process safety. But as I say, we also have the luxury of having test laboratories, accredited laboratories, for really getting to understand the flammability and combustibility characteristics of gases, liquids, vapours, and combustible dusts. And we also have the capability of doing chemical reaction hazard testing as well, so calorimeters, DSCs, HAC, all of that sort of stuff. And of course that feeds into the consultancy arm with the sort of advice we can give to operating companies. And we also do a fair amount of bespoke training for companies on many different aspects of process safety, including fire and explosion, which is the subject of today's presentation to you. So you can see there from this slide the sorts of things that keep us busy, earn our money, and hopefully makes the process industries a safer place to work, and of course complying with the necessary legislation. And as I've said before, You know, we have this luxury of having the testing laboratories. So as I've mentioned, fire and explosion properties of all types of substances. We're also experts in electrostatic properties. So again, we can determine resistivities and look at electrostatic ignition probabilities and all that sort of thing. So, you know, we do tend to be able to help industry in quite a large way. So, okay, what we're trying to do here today is give you some information on this subject called Hazardous Area Classification. And really, this subject is all to do with trying to prevent or manage substances and processes that can burst into flame or explode. Okay, that's what we're trying to do. And just a couple of examples that because you'll all be familiar with the fire triangle. So before something can burst into flame, we need a fuel. We also need air or oxygen, and those need to be in certain proportions to create this thing called the flammable atmosphere. Because within Europe, we talk about explosible or flammable atmospheres, and it's this mixture of fuel vapours with air. And that fuel, of course, can be either vapours from liquids, gases, or combustible solids, okay, in the form of dust clouds. And this is just one example where, and then the third part of the triangle is an ignition source. So just like with all of these triangles, if we can take away any one of those 3 points, either fuel or the air or the ignition source, then we don't burst into flame and we don't have the potential for explosion. And Piper Alpha is just one example, which you'll no doubt, you know, as process safety professionals, you'll know all about the Piper Alpha disaster. But one of the things was a deluge system was activated by the gas leak. And this resulted in the ingress of deluge water into a light fitting, which was a protected light fitting, but because we had ingress into it, it was no longer explosion proof. We got an electrical short circuit and, of course, the generation of a spark. Now, I'm not saying that this was the only potential ignition source or the active ignition source for the Piper Alpha, but it's just an example in relation to the topics we've been talking about. Another one that undoubtedly, especially our American audience, will understand is the Danvers plant explosion way back in 2006, where essentially we overheated a flammable liquid created because we left the steam on inadvertently. Obviously that generated vapours. The ventilation system had been isolated, but it's very difficult when we're dealing with fires and explosions to ensure that we eliminate all potential ignition sources all of the time. So of course, you know, under such circumstances where you've got this flammable atmosphere present, eventually, given sufficient time, it's likely to come across an ignition source, and we have the confined vapour cloud ignited by a non-rated fan, and we result in the consequences of that serious event. So what we're trying to do in hazardous area classification is try and prevent this from happening. And of course, these are serious things, so you can envisage that there is legislation present within our nations to be able to deal with these sorts of events, to try and prevent them in the first place, or indeed, if they do occur, ensure that the explosion or fire isn't as bad as it could be. What we're essentially trying to do is break that fire triangle in its simplest form. Now, within the UK, we have a set of regulations called the DSEAR regulations. DSEAR standing for Dangerous Substances in Explosive Atmosphere regulations. So these are substances that are classified as flammable or combustible, and if they mix with the air can produce this explosive atmosphere. And what the regulations essentially require us to do is to carry out this thing called a hazardous area classification, determine where we can get mixtures of fuel vapours or fuel dusts with air, and to determine how big those flammable or explosive atmospheres could be. We'll talk later about what's called the extent of the flammable atmosphere. And basically, the system is built on a yes-no answer, which basically says if a flammable atmosphere is present, then that's a hazardous area. And we go on to define that as a zone within the UK and Europe. And outside of that area or zone, where the flammable atmosphere is below the explosive concentrations, then it's non-hazardous. So we look at where we can generate mixtures of fuel and air, and sometimes that'll be internal to equipment. For example, within a storage tank containing a flammable liquid with a low flash point. If it's an atmospheric storage tank and open to the air, then as we draw off liquid from the tank, we'll be drawing in air, which will mix with the vapours that are given off from the liquid surface, so we'll have a flammable atmosphere. But we look at these hazardous areas and we use a risk-based approach to determine the zonal classification. Now, within the regulations, it gives a definition of hazardous, and what it basically says is if there is any equipment present that could act as an ignition source within that hazardous area or hazardous zone, then the equipment needs to be special. It needs to be protected. And what this basically means is that that piece of equipment, whether it's electrical equipment or mechanical equipment, is constructed to reduce the probability of that equipment acting as an ignition source. Because if it's present within a hazardous zone and it can act as an ignition source, then of course we've fulfilled all requirements of the fire triangle and we will get an ignited event. Okay, so what it's basically saying is within these hazardous zones we need specially protected equipment that is constructed to whereby the probability of it becoming an ignition source is reduced. You know, if I picture that with a normal switch, a light switch in our houses, every time we flick that switch, we generate a spark across the contacts in that switch. So if that switch is present within a hazardous zone and that spark is of sufficient energy to ignite that flammable mixture, then that will be our ignition source and we'll have a fire or an explosion in that piece of equipment. And it's really as simple as that. That's what's required under the UK situation, and Andrew will just give you some idea of what's required in the US situation. Fundamentally, it's the same, but of course the language is different.
So in the US, there's really two overall guiding documents. There's NFPA 497 for any time you're handling a flammable liquid gas or vapor, and NFPA 499 if you're handling a material that has the potential to result in a combustible dust cloud. And if you know your process has these materials, you're required to go through and apply the NFPA code and determine, you know, is this area classified? And if so, per the requirements within NFPA, you're then directed to NFPA 70, which is the National Electric Code, and it has specific requirements based upon the classification that you derive through the methods within NFPA 497 and 499. And it will dictate, you know, what you need to do for an installation within whatever you've determined that area to be classified for it to be a safe installation. It's a lot more of judgment calls and, best understanding of processes, as opposed to a yes/no list-based process. It involves kind of a holistic approach of looking at process, size of process, potential leak points, what the material itself is, does it have exceptionally high ignition energy requirements, or is it something that can write really low? You go through, you make these adjustments, you find what NFPA recommends as a classification zone, and then you would apply that to your process. And then within that applied zone, take the requirements from the electrical code and make sure anything that's within that zone meets all the requirements of the NEC. Okay.
Okay, thank you, Andrew. So, once we've done that hazardous area classification, the output is generally a drawing. So this is a drawing for an atmospheric storage tank, and which illustrates the different types of zone. Because I say it's based upon the likelihood. The zone is based primarily on the likelihood of that flammable atmosphere being present. So if in this case we've got the contents of a tank, it's containing a liquid with a low flash point. If the flash point is lower than the ambient temperature, then that will give off sufficient vapours that will mix with the air, because the tank is open to atmosphere through a PV valve and what have you, and we'll have a flammable atmosphere for all intents and purpose continuously within there. The only time when we won't have a flammable atmosphere within that tank is if we have a cold snap and the temperature of the liquid falls below the flash point. But outside of that, around the vents, for example, around the PV vent, that will most probably only be giving out vapours when we're filling the tank, when we push those vapours out. So in normal operation, we expect those vapours to come out of there. But once that if it's static and we're not loading or unloading from the tank, we'll be in a static situation. And then we have what's called another zone outside, which is essentially related to if we overfill the tank or spill the tank or whatever. So once we've got that zonal classification, this sort of drawing, and we tend to do those in both plan and elevation, that means if we were to put any equipment like a pump within that tank bund, this lets us specify that equipment appropriately in terms of its likelihood of becoming a probable ignition source at the same time as the likelihood of having the flammable atmosphere present. And that allows us then to hopefully ensure that we don't fulfill the fire triangle. Now we've got the regulations in the UK, which are based upon directives from Europe, even though we've left Europe, the UK at present, but they were based on the ATEX directives, and that's just because EU worked that way. So what happens in Europe is directives are developed, and then once those directives are agreed, and the directive for this subject was called the ATEX directive, that stands for atmospheric explosive, okay, in the French. I won't do my French accent, it's not very good, but it stands for atmospheric explosive. So we had the directives, and then what's required is for each member state within the European Union is to develop its own national legislation. And the legislation that requires this in the UK is the DSEA regulations, the Dangerous Substances and Explosive Atmosphere regulations. The regulations give us the high level requirements that we need to do, but the regs do specify, for example, that we must do a hazardous area classification. But the detail on how to do hazardous area classifications and how to determine equipment categories and that is generally done within standards. And I've given you there the two most applicable standards, 60079 for vapours and gases, part 1, and part 2 for combustible dust. But on this subject, there's about 40 60079 parts that give us help on all manner of things like, electrostatic hazards and various other forms of ignition sources and different types of industry and so on and so forth. Now, we've already talked about what the flammable atmosphere is. It's this mixture of vapours with gas, and they've got to be within the proportions that we know about, being the lower explosive limit or the upper explosive limit. So if we've got insufficient air, we're too rich to burn, we're operating above the UAL, the upper explosive limit. If we've got too much air, because ventilation is very good or whatever, we could be operating below the LEL. So, you know, we've got liquids that can generate vapours primarily due to temperature on the flash point, or we can do it from a vapour concentration point of view. But obviously, as we all know, those limits can widen as the temperature increases. Okay, and that's all that is illustrating. Now, to be able to do this job properly, we need to understand properties of the substances that we're dealing with. And when we're talking about gases and vapours, these are the sorts of data that we need to understand. So flash point for liquids or gases, the flammability limits, the auto-ignition temperature. So similar to the flash point is ignited by a flame or a spark ignition, where the auto ignition temperature is a hot surface effect. So the auto ignition temperature is a lot higher generally than the flash point, often in the hundreds of degrees C. The gas group, so we tend to classify various gases and vapours into one of three groups. But this really relates to the ease of ignitability, or the minimum ignition energy necessary to be able to ignite certain substances. And of course, if we're looking at where our flammable atmospheres can be, then vapor density is important. So when we're doing our hazardous area classification and developing those drawings, if we're dealing with a buoyant gas like hydrogen, for example, any release of hydrogen will be buoyant, will mix with the air, so the flammable atmosphere will be a buoyant flammable atmosphere and go up, where for solvent vapours, typical industrial solvent vapours, the vapour density will be heavier than air, so they'll tend to sink to the ground. So of course that will impact our hazardous area classification. Now, I've talked there about gases and vapours, but of course powders or combustible dusts can burst into flame or explode. But generally, if there's good mixing, good suspension in air, so clearly, therefore, just as with vapours and gases, we need to have a powder that is capable of acting as a fuel. And by that I mean it's capable of reacting with oxygen, because that's really all combustion is. An ignited event is a combustion reaction. All combustion reactions are the same. It's the material reacting in oxygen. So if that material is already fully oxidized, then it won't be able to react with oxygen. It'll be inert. So something like chalk or sand or cement, fully oxidized substances cannot form a flammable or combustible cloud. The concentration's got to be within explosible limits, what we call the minimum explosible concentration of dust in air, very similar to the LEL and the UEL. But because we need that suspension in air, what we found is that we need to have a particle size distribution of the powders to be less than 500 micron. Less than 500 micron has an effect on the reaction dynamics of the combustion reaction. It also has an effect on its capability of generating a dust cloud, getting this intimate mixture with the air. Okay, and of course we've got to have an energy source that is above the minimum ignition energy of that powder. And all of these things, if you listen to some of our previous webinars, and undoubtedly we'll be doing another one very soon, that would take you through exactly how we measure these things. Because for vapours and gases, you can get a lot of information simply by going to the standard chemical engineering and scientific literature. But for combustible dust, because it's very particle size dependent, really it's testing. We can't really calculate the flammable atmospheres and things like that. We need to actually do the testing itself to get that sort of information, which is what's illustrated here really. So we have tests where we can determine whether or not a powder will be combustible. That's known as the AB classification, where we create a dust cloud and put a very large energy source through that dust cloud and see if that will explode or not. We can determine the minimum explosible concentrations, particle size, the minimum ignition temperatures of both a cloud and a layer of powder, and its electrical resistivity. So these are just some of the tests that are typically that we use to get an understanding on the substance as to how likely it is to form a flammable atmosphere and how easily it can be ignited. And again, there's guides out there for us. There's standard, another part of the standard that tells us about, you've seen these before, I presented them before, but there's also industry codes as well. So the Energy Institute in the UK, which is essentially looking at the storage and safe handling of highly flammable liquids and liquid fuels, Model Code of Practice, Part 15. You'll have similar things in the States, which Andrew will take you through now.
Yeah, again, within the states, majority of all the information is contained within the NFPA requirements. And I'll walk you through for gas and vapors in 497, definitions, classifications, provide you with those example diagrams, and then give kind of explanatory material walking you through why those diagrams may apply to your process, or if you know there's a reason for it not to apply and something else will be helpful. And then again, directs you to NFPA 70, which will tell you, all right, you're going to have electrical installations in these areas that you've determined need to be classified. Here's what you need to do to ensure that those electrical installations don't provide a potential ignition source. And then it's an identical process for powders with NFPA 499 instead of 497. And again, pushing you through to NFPA 70 and the specific requirements. Okay.
So you can see it's very similar. So, you know, what are we trying to do? What's the philosophy behind this hazardous area classification? We're talking about zones, and I've said before these are risk-based zones, and the risk-based because we're looking at the probability of a flammable atmosphere occurring simultaneously with the probability of an ignition source being present at the same time. Okay, so if you like, what we're trying to do from a risk point, a risk equation is we're trying to reduce the risk of having an ignitable event, and that risk is a combination of the likelihood of having a flammable atmosphere present and the likelihood of having an ignition source present at the same time. So therefore, clearly it means that if we've got a flammable atmosphere there present continuously, like for instance in the headspace of a tank with a low flash point liquid and an atmospheric storage tank, then because the flammable atmosphere is there practically continuously, that risk, most of the risk reduction comes from reducing the probability of an ignition source being present. If, on the other hand, we only have the flammable atmosphere developed on occasions because we spill something or we have a leak and it gets out of the pipe and it mixes with the air, but those occur a hell of a lot less frequently than you know, just having the vapors above an open source of liquid, then of course most of the risk reduction is achieved by not having a flammable atmosphere present for very long at all. Yeah, so of course then any potential ignition sources don't need to be as protected. their probability of ignition can be higher. Okay, but it's worth saying within hazardous area classification, what we're looking at here is we are looking at what we're trying to assess is what I'll call operational weeps and seeps, where we expect flammable atmospheres to be generated. We expect a flammable atmosphere to be there in the headspace of a container above a liquid with a low flash point. We expect occasionally pipe flanges and things to leak. And if they do leak, then we'll generate a flammable atmosphere. What this approach is not aimed at doing is considering, for example, a pipe being impacted and breaking in two, a guillotine fracture of a pipe. So large considerations like that, where major accident hazard considerations, they'll be dealt with in other risk assessments, because we can't protect ourselves by just having the zones on such a large release would be so large we wouldn't be able to ensure that there's no ignition sources present. For example, if I had a large LNG storage tank and I got a hole in that tank, the flammable atmospheres produced can be measured in hundreds or thousands of meters. There's no way that we can ensure that all potential electrical and mechanical equipment over such a large distance can be made protected. Okay, so it's looking at what I call operational weeps and seeps. So what's the approach then to actually determining these zones? What we've got to find out, we've got to understand the materials we're playing with, whether or not they're capable of bursting into flame or explosion and how easily, but we've got to identify where these flammable atmospheres can be. And generally they can be either inside equipment, or if equipment fails, we have leaks or we have spillages where we can get. So we need to identify these sources of release. Obviously, any vapours that are released from those sources will be dispersed due to ventilation characteristics, either natural ventilation or specific forced mechanical ventilation. Our next task is to determine what we call the grade of release. Is that flammable atmosphere there continuously? Is it there in normal operation? Or is it there infrequently? Or you can think about it another way. Continuous is obvious, something like a flammable liquid being present at temperatures above its flash point in a containment system would be continuous. A vent, for example, will only generate that flammable atmosphere when the vent is in operation. So when we're filling the tank, we'll be pushing vapours out from that tank. When we're emptying the tank, sending it off to process, we're pulling air into the tank. Okay, and then infrequently would be taking care of our spillages and our leakages. Once we've determined that grade of release, that automatically points us to the zones. So a continuous release becomes either a zone 0 if it's vapor or gas, or a zone 20 if it's powder. A zone 1 is a primary zone, or zone 21 for dust. And our spillages and leakages is a secondary zone, zone 2 for vapours and gases, or zone 22 for leaks. And Andrew will now illustrate how that's done in the US.
So in the US, the start of the process is the same. You're looking at your process and you want to know where is there the potential for there to be a release of combustible material. And then you go and you gather information on the facility history and the process information. Facility history, you want to look at, is there a tendency for there to be, leaks during maintenance activities? Is there a high rate of spillage. Is there anything in the historical documentation of this facility that leads you to believe that releases are going to be more likely than they would be on the average? And then within process information, you want to look at volumes of materials being handled, pressures that the process operates at. Is it a high pressure? In that case, it's going to be a larger zone than if it's a low pressure or an open system. You want to look at flow rates. You want to look at all of your process parameters, and that will help you dictate, what makes sense for our zone. Then you go and there's the classification diagrams listed in NFPA, and you compare release source and your process details, and you make sure you find one that matches that. And then you match up your diagrams looking at your likelihood of ignitable mixture being present, your potential for combustible material to be transported further. If you have trenches, pipes, conduits, ducts, something that can travel that combustible atmosphere away from the primary leak source, you want to make sure that you're using a classification diagram that represents that as well. And then you document that using the class, division, or zone of the material, the name of the combustible material, respective material group, and either an auto ignition temperature or an appropriate design T code, which we'll get into later in the presentation. It's the same for combustible dust as it is for combustible vapors, liquids, gases, and just which NFPA document you're using to help walk you through the process. Okay.
Okay, and as I've already discussed the zonal classifications before, this just gives the proper definitions present within the standards, but hopefully you can see, and we use the same system in the UK or indeed in the US if we're talking about zones. But in the US we have additional definition which Andrew will take you through.
Yeah, so US started with class and division before adding the zones. That's a relatively recent move to become a little more in line with European, but most places still use a class and division system. It's fairly simple. Class 1 is going to be explosive gas or vapor atmosphere, and division 1 is going to be present during normal operation. Division 2 is under abnormal conditions. So lines up a little bit with the zones, but rather than having the 0, 1, 2, division 1 kind of encompasses your 0 and your 1, but it's a different requirement technically. So if you've got something that's classified for a zone and you're using a division, it doesn't quite line up. You need to make sure your equipment is class 1, div 1 certified. And then same with class 2 for normal operation, or there being combustible dust present that could be stirred up. You've got an inch thick layer on, say, the ground of your shop around your routing machine. If someone were to step and they can stir that dust up and there's an electrical spark in the area, there's the potential for ignition. And then your class 2, division 2, it's only likely during abnormal conditions. So this would be if you've got a secondary event occurring, or there's a failure and a release during a maintenance activity, then you would expect to see your dust there. It's just a different way of viewing it as opposed to the zone method. But I think as the US moves forward, they'll probably end up stepping away from classes and divisions and moving more towards the zones in the future.
Okay, thank you. So just to reiterate, we've got these different types of grade, whether the explosible atmosphere is there continuously or very frequently or for long periods, whether it's periodically there or on occasion during normal operation, or we only expect it because we're having leakages or spillages or some form of malfunction, this sort of thing. And again, very similar in the US, although there appears to be some form of quantification to the volumes of materials.
So within the US, we don't really look so much at grade of release as opposed to a size, pressure, flow for the process involved, and let that kind of dictate some of our volumes. We have the similar approach of combustible atmosphere always or expected present during normal operations and then occasional, but it doesn't feed in as much as your process equipment and piping details that will directly impact which methods of classification diagrams you're going to be looking at. Okay.
Okay, thank you. So it's all right having words that describe these grades of release, but these can be translated in the standards into hours. So it gives you some indication here. So when we're talking about a zone 0 or a zone 20, it's continuous. So we talked about it being there frequently or almost most of the time. What we're actually saying is these sorts of figures, more than 1,000 hours per year. And there's about 8,500 hours in a year. So an eighth of a year, we've got that flammable atmosphere present, or more than an hour per shift. Whereas a secondary release resulting in a zone 2 or a zone 22, taking account of spillages and leakages and these sorts of things, less than 10 hours per year or less than a minute per shift, this sort of thing. So we just try and help ourselves there. So actually defining the zones is pretty easy once we've got an idea of the grade of release, because the grade of release determines what the zone is. The only thing that changes the extent of that zone is if ventilation is there and it's good and it has good dilution and it has good dispersion characteristics. So, for example, if over an open container of flammable liquid where it's a continuous grade of release, okay, if I've got mechanical local exhaust ventilation that's been designed where the airflow effectively reduces the vapor concentration to less than 25% of the lower explosive limit, then it remains a continuous grade of release, but the zone extent can be what's known as zone 0, negligible extent. So if you like, the size of that flammable atmosphere is reduced down to a very small volume by virtue of having good ventilation and good availability of ventilation. But there are different ways of determining the extent of the zones, the size of these flammable atmosphere zones. The easiest approach is the example approach. So that diagram I showed you before of the atmospheric storage tank with the zones around it, that, if you like, the exercise has been done by the industry and that's the accepted way. So you can simply, if you've got a atmospheric storage tank within a bund or a dike, and it's a low flash point material, you can simply, your hazardous area classification is as simply as just taking that out from the standards or the guidance that's available and using that. You don't need to do anything else. Okay, but there are calculation methods as well that can be used where you can determine things called release characteristics and fancy things like this, where you can actually calculate or in fact use consequence modeling software to determine the extent of a flammable cloud, its shape and so on and so forth. So there's different ways of doing it. The simplest though is if it's already been determined by somebody else, is using that. And a lot of the guidance in Europe and in the UK, as already hazardous area classifications around typical pieces of equipment, mixers, pumps, vents, tanks, reactors, things like that, are already being done. You just need to check that your situation is essentially identical to the situation of the example that's given.
All right. Within the US, we don't currently have that calculation exemption. It's all going to be based on diagrams and best understanding of the potential releases using kind of a consideration of what the material is, the vapor density of the material. So is it lighter than air, heavier than air? What the LFL is, your processor storage size, your size of your release, and your ventilation. And then you take that, you look at that, and you apply the diagram method and adapt that to what your facility needs and looks like.
Yeah, so we've got exactly the same sort of thing for dust. It's more difficult to calculate, but you can actually use the knowledge when some of these events have happened. So for example, if you do have a spillage, you drop a 25 kilogram sack of powder on the floor when you're charging it, you simply need to, to get the extent of the zone 22, for example, is just visually look at how far the dust has been deposited over. Is that 1 meter, 2 meters, or 3 meters? This sort of thing. Okay, but it's more difficult to do from a calculation point of view. It can't be calculated. We need to use other sorts of extents.
Yeah. So the process for dust zones within the US is similar to the vapor and gas. Of course, what you're looking at in terms of what affects your zone changes. You still looking at, properties of the material, but now you're adding bulk density, particle sizes, particle density, what pressure it's stored at, the size of a leak opening. Is it a release in the side of a super sack? Is it a pressurized pneumatic conveyance system that has a pinhole, or a slightly bigger leak in a transfer point where it's a flex connection? How much can be released? Do you have dust collection in the area? What your housekeeping process is, and the potential for the presence of a hybrid mixture. Do you have combustible gas and vapors mixed with your combustible dusts? Because that will require a different type of classification.
Okay, so as I said before, ventilation obviously has an impact on the size of a flammable atmosphere and the sizes of those zones. So as I said, you can use high ventilation rates as reducing that zone down to negligible extent, so which basically means you don't need to provide any protected electrical or mechanical equipment in there. But we also stipulate that's from a dilution point of view, that there's sufficient air to dilute those vapours or dust clouds down to a negligible extent. But we also have a thing within the ventilation that we need to look at what's called the availability of the ventilation, which basically means, is the ventilation always on? And if it's not always on or not performing to achieve the performance standards we want, then of course the process doesn't run. So there's some interlocks in the system and this sort of thing. But there's tables in the standard. It's detail I don't want to go into today really, but obviously ventilation has an impact. So just to summarize this bit of it, within the UK we look at zones, which is the move that's starting within the states. You're starting to use zones, although you're still using classes and divisions, which is fine, but effectively it's doing the same job. Yeah, and these are just examples of when, once we know that grade of release, it determines our zone. And it's a similar sort of thing for dust. These just gives examples of where we would have a continuous grade of release for a dust for a zone 20. And it would generally be, for all intents and purposes, it will always be within the internals of equipment. and secondaries because we're spilling stuff or having leakages from pneumatic conveying systems or this sort of thing. Yeah, it's just no different. So hazardous area classification is important, and within the UK and Europe, what the standards require us to do is to produce some what we call zone drawings. And as I said before, because vapor density is important, that will have impact the drawing. So that means we tend to produce these drawings in both plan and elevation modes. Okay. We can put those on, and then those are useful then out in the processing operations for your operators to ensure they know where the zones are. But there's different ways of doing it. You can start painting lines on floors and things like that. So there are specified recommended zone markings for the different types of zone. The standards require that they're used, but really it doesn't really matter. It doesn't change the extent. And you can see here a plan drawing of a quite complicated processing unit. But this is what you'd expect as the output. Now again, right at the start we talked about, there's another example here, right at the start we talked about once we've got these zones, then what we're saying within that zone, that is hazardous. And if we have an ignition source within those zones, we can burst into flame or explode. And therefore, within those zones, any equipment needs to be protected. And that's where we'll be moving on to very shortly. So once we've got these drawings, once we've done our hazardous area classification, we can then decide, is there any equipment present and is it appropriately protected to reduce the probability of that equipment acting as an ignition source. And clearly, once you've done one of these reviews, then of course, within the legislation in the UK, you're expected to review those reviews every now and then. Okay. So obviously, if changes occur on the plant, you're putting in a new process or this sort of thing. You're changing the substance. You're changing one of your substances. You're going from a granular product to a finer, dustier product. You'd be expected to review your hazardous area classification document appropriately. But once we've done that, once we've set up, we've got our hazardous area classification, then we've got to make sure that any electrical or mechanical equipment that's present within those zones needs to be specially protected. Now, there's different ways of killing a cat. There's different ways of building electrical apparatus or indeed mechanical equipment that can ensure that the flammable atmosphere is not ignited. And typically in our industry, you'll all have heard of flame-proof equipment and intrinsically safe equipment, but there's different ways of doing it. And some of these different ways are only applicable to specific zones. Okay, so certain equipment can only be used in certain zones. Other equipment can be used in all of the zones. Okay, now as well as that, and that's all associated with, if you like, the spark ignition source of that equipment. So how that equipment is built is to try and avoid the flammable atmosphere coming into contact with any sparking equipment. But you've also got to remember that hot surfaces can also ignite vapors, gases, and dust clouds. But again, you can build electrical and mechanical equipment, design and build equipment that only generates maximum surface temperatures. And provided those temperatures are below the auto ignition temperature or the minimum ignition temperature for dust, then it's safe because that equipment can't impart sufficient energy. Now, when we're dealing with dust, we talk about a maximum surface temperature, maximum allowable temperature, and we quote that as a so many degrees C. For vapours and gases, we work on temperature classes. So what we've essentially done is taken the range of potential temperatures and grouped them into 6 classes, T1 to T6. And we can take the information from the auto-ignition temperature and pick the appropriate temperature class. So once you've done this job of hazardous area classification and you understand the properties of your substances that you're working with, if you then need to go out and procure equipment that is suitably protected, you're able to do so. Okay, because we know what zone it needs to be in, we know what substance it's gonna, and we know the, how much energy is needed for that equipment to act as a potential source of ignition. So when we go to the shops to procure this sort of equipment, we can make sure that when the equipment comes back, we can check that it is appropriate for the zone, for the location in which that equipment is going to be. There are other methods of doing it, one of which is called ingress protection. So this is essentially sealing the potential sparking components within an enclosure that is capable of not allowing the flammable atmosphere into it. So if we've got an ingress protection of say 65, that means it's dust tight, and it's also, it won't allow water in from a water jet, for example. So there's different forms of ingress protection that we can get, and that's illustrated in the next slide. Yeah, so the first digit is to do with, and that's acceptable for different zones. So for a zone 20 or zone 21 for dust, then as long as it's IP6, so it's dust tight. But for a zone 22, it can be an IP5X if the powder's not conductive. It gets a little bit complicated, as you can imagine, but there's different ways of doing it. Okay, and then when you get your equipment back from the shops, it's just an example of those temperature classifications I was talking about, which are the same whether you're in the UK or you're in the US. Okay, once you've got your equipment back and you're going to install it, the nameplate and the piece of paper that comes with the equipment has markings such as this. Okay, so it's telling us that we can ignore the first two because they're associated with the notified bodies, and it's all associated with the people who manufacture this sort of equipment. But then the rest of the information, unfortunately, what happened with, if you remember, I talked about these directives being developed, and the way directives are developed is we get committees of experts together and they come up with a solution to a problem. And in the ATEX directive, it was done in two ways. There was two committees. One was looking at protecting workers from fires and explosions involving dangerous substances, which is the subject of the DSEA legislation. The second committee was looking at the people who manufacture this special protected equipment. Okay, the problem is the two committees didn't tend to talk to each other. So although DSEA and that ATEX directive talks about zones, the equipment manufacturers don't talk about zones, they talk about categories of equipment. So unless you know the rules about categories of equipment, you can't necessarily determine that the zones are applicable. And this is what this slide is designed to illustrate. So for example, the end marking here, which is GB, that is telling us that this equipment is for use in a gas or vapour environment, not a dust environment. If the equipment was for use in a dust environment, it would be D. And then the B relates to the zone. So they talk about G, A, B, C. The ABC relates to the zone 0, 1 or 2. And if it was dust, it'd be DB, it'd be zone 0, 20, 21 or 22. Okay? And the rest of the markings are to do with the temperature classification there, T4, which was within that range on the table I showed previously on that one. So T4, the maximum surface temperature that equipment can produce due to its manufacture is 135 degrees. So that's saying basically that the auto-ignition temperature of the gas or vapour that's involved here is greater than 135 degrees C. Okay. The EXD, that is telling us the type of explosion protection. And the equipment categories come in 3 categories really. Category 1, 2 or 3 equipment. Category 1 equipment is used where the probability of it acting as an ignition source is extremely low. Basically, the equipment cannot act as an ignition source under normal operation, under expected malfunction, or under rare malfunction. Whereas a category 3 piece of equipment won't act as an ignition source in normal operation, but could if it malfunctioned. Okay, so of course that relates to the zone. So it's all right having a electrical piece of equipment that is category 3 equipment, because that's for zone 2 or zone 22. But remember, under those zones, the flammable atmosphere is present on very rare occasions or for very short periods of time. So the likelihood from a risk point of view of having the flammable atmosphere present simultaneously with the ignition source reduces the risk down to a level that we're happy with. And this just shows within the UK, you're required to give information when you go into a building or a room that has these hazardous areas present, that staff are alerted to the fact that that is the case. The idea here is to say, you know, if you're going to go into that room to do some work, then, oh, hang on, it's got the EX sign on it, that tells me it's special. You know, let's just stand back a bit and have a think, because I may need to follow specific procedures or use specific tools or have specific supervision or whatever before I work on this. So hopefully that's the end of the slideshow. I'm sorry we've gone beyond an hour. Hopefully you've found it interesting and useful to you. I think you've also found that although the language, if I could put it that way, is different between the US and Europe, the intent of what's required and the precautions that are necessary are very, very similar. Now, each of you will have, because you've registered for this webinar, and in fact, any colleagues who may have registered for it but not been able to attend it, you will in fact be sent a link to be able to pull this presentation up again. Will essentially be a link to a recording, so you'll be able to hear my dulcet tones and Andrew's dulcet tones once more and see the slides. So on that, I hope you found it interesting. Have a good rest of the day, and I'll see you again on the next time we do a webinar. Goodbye and enjoy your day.